So next speaker I'm pleased to introduce is the chair of the Computer Science Department at UC Santa Cruz, Jim Whitehead.
All right. So it's a pleasure to be back here at UC Irvine and to be able to tell you a little bit about some of the research work that I've been working on over the past 2 years. I'm going to be describing a game, a software engineering game. And it's not just a software engineering game, but it is a formal software verification game. And so you might initially think that this is an oxymoron at face value. Anyway, I'll kind of walk you through how we got there and what some of the main design considerations are that we dealt with. Here's a list of the major collaborators we've been working with, and I especially want to point out the first one, Heather Logus, who has been the lead game designer on the project. So formal software verification, this is an approach where you make very formal mathematical descriptions of software systems, and once you have this formal model of your system, you're then able to pose questions to that model, and if that model is an accurate representation of the system, then those questions will tell you increasingly useful information about the properties of the system, such as freedom from certain classes of error or certain properties that the system meets with respect to its requirements or specification. From a practical standpoint, there just are not a lot of formal verification experts in the United States, and order 1,000 people maybe who know this topic extremely well. If you're going to do it for real, it's extremely time consuming. Those experts are very expensive people. As well, they're not all necessarily available to work on one specific software verification task. And so as a result, when especially the Department of Defense looks at wanting to use formal software verification techniques, they realize that there are these hard scalability limitations. Even if they could get all of the experts to focus on doing a formal verification of one system, which is doubtful, it would still take too much time and too much money to be able to do that. So there's real desire to scale formal software verification. So, as a result, DARPA is really interested in this question of scale. How do you make software verification work, certainly on larger systems, but also just make it so that you can get more out of that pool of experts. So kind of the insight behind the program that they developed was this notion of, well, what if you could bring in lesser skilled people and have them contribute to a formal software verification in a non-trivial and useful way. So that was the basis of this crowdsourced formal verification program. And even though the title is crowdsourcing, really the particular form of crowdsourcing they were interested in are games. There's this term out there, gamification, which is sort of a very lightweight way of adding game mechanics on top of some existing activity. And what they were really interested in this program was a deeper activity, one where you constructed games that very deeply engage this question of doing formal software verification. And so I think the better term is this games with a purpose. WAP, I guess, is the acronym there. Really the goal is to have human game players do tasks that computers cannot do well. And so this sounds obvious, but really is fairly challenging. A lot of what we think of as hard puzzles or hard games really end up being tasks that computers can do pretty well. It's just that they're also hard for humans, and so humans enjoy doing those puzzles. So if you think of, say, Sudoku, which is a very popular kind of puzzle game, computers are actually fairly good at solving Sudoku puzzles. So if so Sudoku is good as a game, but it wouldn't be good as a game with a purpose because you could just have a computer, pump out answers to these Sudoku problems to the cows, until the end of the day. So the goal here was to find some aspect of formal software verification where computers couldn't do it well, but humans, due to their properties of how they think and perform mentation, could actually contribute in a positive way. So the crowdsourced formal verification program led to the creation of a number of games. One I'll be talking about is this one, Xylem, the Code of Plants, which we developed at UC Santa Cruz. We ended up focusing on loop invariants. those of you for whom this concept is a little rusty, which was certainly myself when we started, what is a loop invariant? Well, the idea of a loop invariant is you have a loop, a for loop, a while loop, a do loop, and you want to be able to describe formally, mathematically, how this loop behaves. And so you pick a point in that loop, and then you create a mathematical statement that has a closed form kind of property to it where you're describing what that loop does in a way such that that description is always true and also doesn't have this sort of transfer equation form where you're not just saying, well, the current state is the previous state, plus some transfer. So you really want to avoid these transfer equations, and you want to be able to describe it in this kind of invariant way, not varying way. So for example, if you see in the loop that say some variable, x is always less than 10, that's a reasonable invariant, although it may not be the most descriptive one. Or you might notice that, say, one variable is going down while another one's always going up at the same rate. And so then those two variables together always equal some constant. So those are examples of very simple invariants. They can get quite complex. And so it turns out some development of loop invariants can be automated. So there's this DICON system that's one of the better known ones for having computers automatically come up with loop invariants. However, these systems tend to produce a lot of fairly trivial invariants, and they also don't tend to be able to capture the most complicated ones. So here's a task where a human being, if they sit down and study it and they can use some intuition and insight and experience, they can end up being much better at developing these loop invariant expressions. Loop invariants are important for software verification because if you're going to formally model your software, you need to model certainly all the straight line sections of code, but you also need to model the loops where most of the action in the code occurs. Now these loops, if you're only able to model the straight line areas, then your formal software verification isn't going to be as useful. Your model of the code is not going to be rich enough. So it's usually the case that if you're able to do better with these loop invariants, then you're able to push the model forward, you're able to get richer results out of your formal verification. So with our game Xylem, our goal was to create a game where players create loop invariants. So on the face of it, sounds fairly challenging, but there was this extra challenge factor, which is that players are not allowed to see the source code. The military, DARPA, was concerned that at some point they would be not just having open source software used, but they would actually have militarily important software, and they wouldn't be wanting the game players to have direct access to that source code. And so this really left us with this challenge of, well, how can you understand the semantics of a loop without actually seeing the code of the loop? And this, on the face of it, seems impossible. And the proposal effort for this program was really exciting. I normally, at least in my experience, when I write a proposal, I have a fairly firm idea, and I'm trying to sell the funding agency on this. Here, there was this kind of very hard problem that was handed down, a very short period of time in which to come up with something, and it wasn't clear that a solution existed at all. And there's this saying that some problems are DARPA hard and others are DARPA impossible, and it wasn't clear to us whether this was DARPA hard or DARPA impossible. We had these meetings where we would meet for like an entire afternoon and do brainstorming, and we'd have nothing, like literally nothing at the end. But finally we did have an insight, which we've been doggedly following ever since. And the insight was to only provide the values of the variables. So instead of thinking about loop invariant synthesis as some kind of a static code analysis activity where we're trying to understand the source code, instead provide players the values of the variables at different points throughout the loop, and hope that the player can somehow intuit from these values what the behavior of the loop is. So we're able to use a fairly, actually an extremely sophisticated back-end tool produced by the French Atomic Energy Agency. It's a plugin for their FrameAC tool that does a static value analysis. And so the tool is able to develop synthetic variable values just based on a static analysis of the code and doing a kind of symbolic execution of it. Very handy when your partners in this have this like super sophisticated technology, and we were able to leverage that to come up with these reasonable but still synthetic values for the variables in the loop. So this then turned this process of finding loop invariants into an inductive reasoning task. So, just given a set of variable values over time, could you intuit, that is, could you induce what the behavior of the loop was in such a way that you could write something down meaningful about it? So when we went into this task, there were a number of games that provided some insight. Zendo is one that's not especially well known, but you have these cubes, and the Zen master puts the cubes down, and then people have to make guesses about what rule it is that these colored pieces end up following, and so it's an inductive reasoning game. And there's actually relatively few of these inductive reasoning games out there, so we studied that one quite hard. But then there's other ones like the Fold It game, which is perhaps one of the most well-known games with a purpose. There's this one, Dragon Box, which just by looking at it, you might not tell, but this is a game about algebra and learning algebra. And over time, the symbols get more and more directly mapped to typical mathematical symbols, but at the beginning, that tries to hide the mathiness, and so that was important for us. And then this other game, Space Chem, which it sounds like it's about chemistry, but it's really about making finite state automata to do various things. And so all of these games ended up providing different lenses on this really challenging design problem. Okay, so at this point, we come here and see if my mousing skills are good enough to get this video going. So in the game, let's see, maybe I'll kind of provide a little bit of pause here. So in the game Xylem, your task is to be a botanist who is exploring this island which has mysteriously appeared off of the coast of California. And on this island, there are a number of unusual plant species which you find there. And these plant species have varying numbers of flowers on them. And it turns out those flowers end up representing the variables within a loop. So a red flower might be variable I, and the blue flowers might be variable J. And you then go around the island looking at these various plants. You take a look at the numbers of flowers, you come up with a mathematical description of it, and then you're able to move on to the next plant. So here we are at the beginning, and you have this desk where you're able to get a little bit of background on the island and your task and why you've been invited there. So you kind of read about it, and then you go ashore onto the island of Miraflora. The island is divided into various regions, so we're able to divide the problems up into various parts. This is one area called Lambert Mountains, and each of those flowers is a particular kind of problem. And so here is one of these plants, and what you see are what we call various growth phases on the plants, and each growth phase represents a different point in the iteration through that loop. And you then see that the flowers have varying numbers of, or the plant has varying numbers of flowers at different growth phases. And just by looking at this, you can say, well, okay, there's different kinds of relationships that might exist here. And so on the very top, you see, okay, 18:9, okay, that's looks suspiciously like a divide by 2 there. This red one, 18:17, so that looks like an individual decrement. And so based on your intuitions, you can start seeing like, oh, okay, maybe there's some patterns in there. And you're able to swipe back and forth through them to take a look. So this game was developed for the iPad, and so we took advantage of that touch and that tangible capabilities. And then there are also these tiles here, which we call bonus tiles, but these are actually initial values that are coming in. So these are the initial values of some of the variables as you enter into the loop. And the static analysis is able to provide those to us, and then we pass those along to the player in hopes that they'll be useful for their analysis in some way. Okay, so you swipe along, you sort of notice a particular relationship that might exist, and okay. Doing that, you then transmit it back to base camp. So there's a little snippet of a story that explains what's going on the island. And then you get into this screen here, which tries to give you some feedback on your solution. And so this one says, okay, number of flower types used, so you ended up using 3 different types of flowers in your solution, and it turns out kind of the best people doing that problem also use that many variables. And then the number of bonus tiles used 1, and the best players were also using 1. So this gives you a kind of histogram where you're able to compare your performance against that of other players based against this model we have of how well or how the goodness of these particular loop invariants. Okay, so I pop back into the presentation. So one of our key design challenges here was trading off this goal of doing a good software verification, while also providing a fun gameplay experience. And so usually games end up taking some problem and they kind of really simplify it and distill it down into its core essence, and a lot of the real complexity in a particular domain goes away. And so in Angry Birds, for example, and it's a pretty simple physics simulation when you get right down to it. They're not exposing the full complexity of how complicated various kinds of mechanical systems can get. They give you a relatively simple one and then base their gameplay around that. For here, every time we would simplify the domain, well then that would limit more and more the kinds of useful things we could say about loops, and therefore it would be less and less useful for the software verification task. On the other hand, as we made things more expressive, then that made it more and more challenging to make a good game. So there are all these trade-offs that we had to make between that, and that was sort of the key trade-off that we've been struggling with the whole time, is sort of meeting these verification goals and meeting entertainment goals at the same time. Okay, so a couple issues that we went into. So one, a big issue in game design is always figuring out, well, who's your audience? Who would end up playing this game? That was always a struggle for us. For meeting the verification goals, we wanted as broad an audience as possible. We were hoping that this would be a sort of a casual game, but as we dove into it more and more, we kept realizing that no, and there's an inherent mathiness to this, that once we made this decision to allow people to essentially have equations and have a math equation editor in this game, that really drove the audience and led us to a place where the people playing the game were really only people who wanted, were comfortable with this math, actually thought it might be fun to spend their spare time writing equations. This is not sort of, everyone in the population. The other thing that we uncovered, and I guess I've sort of always known about it but never really run into it hard, is even among adults, there's still a tremendous amount of math anxiety out there. And so about 1 out of every 15 to 20 adults we gave the game to had this very strong, very visceral, very negative reaction to it because of the mathiness, and it's because the game just sort of really tapped into this deep anxiety and negative feelings around math. The other challenge we had was how to visualize the data. So the problems that you've seen so far are just integers. Integers are important. Some of my favorite variables are integers, but they're not like all of the variables and all of the data structures that you see. And so one of the challenges we had was, okay, how could we come up with a metaphor for representing these variables that would have enough legs that we could handle integers, which are easy, but then also take us into things like arrays and linked lists and trees and so on. And we also wanted it to essentially hide it a little bit. We wanted to avoid just giving you a big table of numbers, although some of our more advanced players request that. And be appealing. We wanted there to be some visual interest in that. So we ended up using plants. The more we looked into plants, the more we realized that there's this incredibly wide array of plants. They have this vast range of how they behave, what they do, what they look like. And one of the nice things from a game design perspective is it means that we could put almost any old plant-like looking thing up on the screen, and it would be hard to say that, like, oh no, that's not a plausible plant, because we could point to some plant out there that really actually does exist, that has some strange properties, and that's somewhat similar. And so in particular, we like this notion of flowers being able to represent the variable values for integers, but we also knew that there were these rhizome-like structures that could then represent lists, and that allowed us to extend things to arrays as well. And so that's just an example of our mapping deployments here. So I touched on this a little bit. So the verification goal is you want to be able to say as many useful and interesting things about these loops as possible, so that you can come up with as many loop invariant descriptions as possible. On the other hand, as you increase expressive power, that also increases the complexity of the interface, and it makes it more and more mathy. And so, in the end, we ended up being really heavily driven by the need to express really rich things, but that also drove us to this really mathy place. Let's see. So in terms of the reward structure, this was kind of showing you that reward screen that we used before. One of the big challenges we had was, usually in a game you know what a right answer looks like. For us, there wasn't any way that we could quickly and easily tell whether the player had a good invariant. We certainly could know whether the expression they typed in satisfied all the variable values that were there. That was easy to do, but it's pretty easy to type in a fairly trivial description. You could say like, x is less than maximum integer. Like that'll pretty much always work, but it doesn't really tell you anything terribly useful about the values, and it doesn't help drive the verification forward. But it wasn't possible for us to really easily reject these kinds of bad invariants or trivial invariants. So we ended up in the game trying to come up with a solution where we developed a model of what a good loop invariant would look like. And I have to say, I think we ended up failing on this, and that even though we spent a fair amount of time coming up with this model, there were a number of fairly trivial ways that people were able to work around it. And the players who started playing our game very quickly saw ways through this, and they weren't terribly satisfied with it either. And so one of our current pieces of work is actually to move away from this kind of approach to one where we're just having the players themselves rate the solutions after playing through the problem. That way, humans are able to use their judgment in trying to determine how well these work. Okay, I think I'm just about done. Let's see. I think I'm kind of end up here. So the game itself, I would say, has had modest success. So we've had about 1,750 downloads. A big spike of this happened right after we released and had a fair bit of publicity over it. But the number, the amount of interest quickly dropped off, and the number of players of the game quickly dropped off as well. And so I think, to me, what this speaks to is, first of all, just the difficulty of creating a game with a purpose that has enough depth that people will want to stay in the game and continue playing the game and want to invest a long period of time in it. I think it also speaks to the challenge of trying to convince people to do such a complicated mathy kind of game as well. So we're in a process of changing the game in some ways to make it so that it provides better feedback to the players, makes it so that we have a little bit better control over the presentation of challenge to players. And we'll be doing a relaunch probably later this summer and see if we can actually achieve that nirvana of a community of people who are active and staying in the game and playing it and continuing on. So with that, thank you very much.
Good question? Let's go over here. Sure.
Are the economics of formal verification such that you could use this game, which is so much fun, plus a small financial incentive to get people to play?
Yeah, that's an excellent question. So I, sort of the goal of this program was to try and make the games and do that. But I think one of the lessons you could take away from this is that maybe maybe this is not quite so fun that would provide you the scalability that you would want. But then something like adapting these tasks to an Amazon Mechanical Turk or some sort of system like that might actually be the way that it would work better in practice. Here it's kind of hard to predict how many players will show up in a given day, but with Mechanical Turk, it's like, well, if you need a lot of verification done, go ahead and put a lot of tasks up. If you don't, not a lot of tasks, and so I think that would be a model that would work better.
Does the system check that the invariants that the players propose are true?
Um,
or at least the data points the player has?
Yeah, so on the back end, we have a two-phase checking. So we do like a quick check to see whether it kind of works relatively well, and then there's sort of a longer process that does a deeper check on that to see whether it's a true invariant across all of the different problem instances. One of the challenges we had is that longer check, I think it could take as much as a minute or two. And so that's just not reasonable in a game. I do something and then I sit there and twiddle my thumbs for 2 minutes waiting for feedback, and it just doesn't work. And then getting the feedback later, we also decided wasn't super viable as well. So we sort of say, do as best as you can on these, and the hope is that the crowd in aggregate over many different problem space in the same loop will be able to do well.
If I submit, say, x is always less than 12, and in growth phase 4, x is 15, will it tell me that right away that I got that wrong?
That's correct. Yeah, it'll be read and it'll give you feedback that that's not correct, and you then can't submit that one.